Okay, good morning everyone. My name is Joan Calvet and this talk is about building a multi-architecture disassembler. And this is a teamwork with my colleagues Nicolas and Cedric. So first thing first, who are we? We are software developers working for a small company called PNF Software. And our main activity is to develop the JEB decompiler, which is a reverse engineering tool that you might know as an Android decompiler. And just to give you an idea, in 2012 we released the major version 1 of JEB, which was at the time only an Android decompiler, but it translates Android application back to Java code. And it came with an interactive UI and a scripting engine. A few years later, in 2014, we released JEB version 2, whose goal was to also decompile Windows Linux executables back to C code for several architectures, x86, ARM, MIPS, including their 64-bit variants. And finally, in 2019, version 3 of JEB came out with decompilation for non-native platforms, such as Ethereum contracts and WebAssembly modules. So JEB started as an Android decompiler, but nowadays we are extending it to make it a more general reverse engineering tool. So first, let's replace the topic of this talk within the context of the JEB native decompilation pipeline. So here, we are not talking about the Android decompilation, but about the native decompilation. So there is a simplified view of the pipeline. The input is a file with native code, for example, a Windows PE file with x86 code, an ELF library with MIPS code, a firmware dump with ARM code. So the first step is to disassemble the file to produce what we call the native model, which contains routines, data, and is an assembly language-based view. And then each routine from this model gets converted to a custom intermediate representation, which will then be optimized in the next step to provide a high-level intermediate representation with types. And finally, the IR CFG is structured to obtain an abstract syntax stream, pseudo-C, and this AST is then modified to obtain the final high-level representation. So that's just to give you an idea about the general workflow. And in this talk, we will focus only on the disassembler step. I will make a few incursions into the next IR steps because sometimes it helps the disassembler, but this talk is mainly about the disassembler. And so the JEB disassembler can be informally defined as a static analysis producing an assembly-based view of all binary, representing what can possibly happen at runtime. And not that we are not talking merely about the translation in assembly of individual machine instructions. This is just one of the features of the disassembler. And so it is intended to be a safe analysis. I will not provide any formal definition for that, but let's just say we want to avoid the following mistakes. So the worst mistake a disassembler can do is to disassemble data. It is especially wrong because there's some kind of domino effect by creating wrong cross-references, branches, etc. And then we want to avoid considering code as data and simply missing code and data. So why do we need a disassembler? First, because this is really the foundation for the decompilation pipeline, as I said before. And in particular, it does several important things like trying to separate code from data in the binary, providing the control flow, the data flow, and also because it builds useful abstraction that the decompiler is going to rely on, like routines, control flow graphs, basic blocks. So of course, as you know, a disassembler is also useful because its output can be directly understood by humans, and especially when the decompilation fails. And to give a bit more context about the development, the disassembler is a custom component we developed over the last few years. It's in Java, like the rest of JEB, and of course, it's always an ongoing project. So most of the logic is architecture independent, that is, this is the same code to disassemble, for example, an x86 Windows file or ARM ELF file. Except for passing of the instructions and a few heuristics I will describe later. It can also handle non-native code, as I said before. And so to give you an idea, what it looks like in the UI, when you open a binary, so you got the routine list, and for each of them, it's native control flow graph, so that's the output of the disassembler, that will be used in input by the rest of the decompilation pipeline to produce the C code that you can see at the bottom. This presentation intent is to go a bit further than the generic definition of disassemblers in textbooks, where they are usually introduced as being divided into two large families. On one hand, there are linear disassembler, which disassemble sequentially all bytes in code sections, and the iconic example of that is objdump. And the well-known problem with that kind of approach is that if data are mixed with code, for example, a switch jump table, this data will be disassembled. On the other hand, there are recursive disassemblers which disassemble bytes by following the control flow, so they avoid disassembling data mixed with code, but the problem is that following the control flow is a hard problem, so they might miss some stuff. So you certainly know these definitions that are given in many reverse engineering books or academic papers on binary analysis. And so in this presentation, we would like to show what happens in a real-world disassembler, or at least in JEB. And hopefully on the way it will show that disassembling remains a complex and interesting problem. So regarding the outline of the talk, we will start from a simple and naive disassembler algorithm. Then we will show the limitations of this simple algorithm to finally present the way we overcome these limitations in JEB. So I think it will be more interesting to start from something simple to explore the problems first, and then talk about the actual JEB implementation. And a small disclaimer before going on, this talk is intended to be a research talk. Many things I would say are certainly debatables and are just the current way JEB disassembler works. And we are certainly not claiming this is the best ever solution to disassembling. So as I just explained, first we are going to introduce a toy example, a simple program that we will disassemble step by step, just to build a first intuition on the problem. So bear with me, please. So we start from a simple C program called secret C. The main routine here checks if one argument was provided, and if yes, then calls a second routine called secret algo with this argument in input as a string. Secret algo is here. It computes a XOR between its string argument converted to an integer thanks to the library routine A to I, and a global constant named secret key defined here at the top. Now, let's say we compile secret C with Visual Studio x86 compiler without any optimization, no function inlining, no symbols. In these conditions, we obtain a Windows executable whose code is almost a literal translation of the C code, and in particular the structure of the executable code will be similar to the source code structure. Now, if we were to give this executable to a disassembler, we expect the output to be something like this. If we let aside the compiler boilerplate code and focus on user code from secret C, we should have two routines. Routine 1 here corresponds to the main, and as there is a test in main, there should be two possible execution paths in its control flow graph, and one of these paths should have a call to a second routine corresponding to secret algo. And this second routine CFG will be very simple. There will be a call to a third routine, that's A to I, and it's a library routine, so it might be statically linked or in a dynamic library. And then there should be XOR with a secret key. So that's just a sketch of what we expect the disassembler output to look like if the input is a non-optimized executable compiled from secret C. Now the question is, how do we get from the executable to this expected disassembly? How do we build the box in the middle here? Before trying anything, there are a few things we need. First, an executable usually comes within an executable format, file format, P, ELF, Mako, depending on the platform, and this file format provides information our disassembler will need. For example, if we process our Windows executable with a PE parser, it will provide us the memory mapping and the entry point. It also provides information on the architecture for which the file was compiled for, here for an x86 CPU, which is a Little Indian architecture. So all this is the actual input of the disassembler, not the raw file. So to give you an idea, in JEB, all our executable file parsers implement the same interface through which the disassembler can access the memory mapping, the symbols, and the entry point. And here are the currently implemented parser we have. The second thing we need is the ability to disassemble individual machine instructions. So let's call this instruction disassembler. And this instruction disassembler take in input a binary blob and produce in output a parsed assembly instruction. And this parsed representation usually contains the assembly mnemonic, the operands, register, memory addresses used by the instruction, and additional information like what are the next instructions that will be executed. So for example, if we give 55 in hexadecimal to x86 instruction disassembler, it tells us that it's a push instruction with EBP register as operand, and the next instruction is the fall through, that is the instruction following this one. Now, ARM instruction disassembler will tell us that these 4 bytes here correspond to a sub-NE instruction with two register operand, and the next instruction is the fall through. And finally, a MIPS instruction disassembler will tell us that the same 4 bytes correspond to a BEQZ instruction, a conditional branch, with 2 operands, and as it is a conditional branch, it has 2 possible next instructions, the fall through and the branch target. So note that the instruction disassembler do not provide anything regarding the instruction semantic, that is what the instruction is doing. It just provides a parsed representation, and the text representation that you see in the UI of a disassembler is a side effect of having parsed the instruction. JEB instruction disassembler implement an interface called iProcessor. You can see here the parser we currently have. So the parsed instructions returned by these parsers implement an interface called I-instruction, which provide access in particular to a mnemonic, the operands, for which we also got an interface, and the control flow information. So that means that the parsed native instruction can be processed generically under this particular interface. So back to a toy example that we would like to disassemble. So for the sake of the argument, let's assume we have a PE parser and an x86 instruction disassembler. These are clearly not easy components to implement, but they are not the focus of this talk. So back to the question, how do we get from the executable to the expected disassembly? So we might first be tempted to try the most basic algorithm, namely linear disassembly, that is disassembling every byte in code section. As you might know, the problem is that Visual Studio often mixes data within the code section, like PE metadata, import-export tables, switch dump tables. So linear disassembly does not necessarily seem the best way to go at first. It makes more sense to try a recursive disassembly that will start from the entry point provided by the executable file parser and then follow the code. So let's try this. Here I represented on the left the memory mapping of secret exe provided by the PE parser. And the first column is the address, then there are the bytes mapped at this address, and we have a pointer to the next instruction to disassemble, initially set on the entry point. So once again, for the sake of the argument, we skip the compiler boilerplate code, and so the entry point is on the main routine. And on the right, we're going to write down the data structures that we are going to build during the disassembly. So we start, we give the first few bytes to the x86 instruction disassembler, and it tells us that 55 is a push EBP, so we add this instruction to a new CFG in a new block, and it also tells us that the next instruction is the fall through. So we increment the pointer, another instruction, we add it to the current basic block, and continue, same thing here. Now, we just passed a conditional branch, jump if not 0. So that's the end of the current basic block, because there are two possible execution paths from there, and so we have two addresses to analyze next, the fall through and the branch target. So here I decided to analyze, to continue analyzing the fall through first, and so we store the target address for later analysis in a bucket that you can see at the bottom right. So fast forward, we disassemble a few instructions starting from the fall through, and now we just passed a call instruction. So that's the usual way to implement a routine call on x86. So we have two addresses to analyze here, the call target and the fall through, when we will come back from the call routine. So I use the same strategy. We continue disassembling the fall through first, and we store the call target for later analysis in a different bucket, because that's a different type of addresses. It's supposedly another routine. So fast forward again, we disassemble the call fall through, and end up disassembling a ret instruction that's a return to the caller, so that's the end of the current basic block. And we have another address to analyze in this routine in the right bucket, so we continue from there to terminate parsing this routine. We continue and end up with no more addresses to analyze for this routine, so we are done with it. And now we can disassemble the other routine, which previously noticed, whose address is in the left bucket. We run the same algorithm on the second routine entry point, and we end up with this. Overall, two routines were found. Routine 1, two possible execution paths. One of these paths contains a call to the second routine. The second routine has another call, XOR operation. So I've let a few details out, but you got the idea. We produce what we expected with a simple recursive algorithm. And it seems that all the magic was in the instruction disassembler, which was providing us, in particular, the control flow information for each instruction. So we might think that it's not particularly hard to disassemble whole executables. We just have to implement an instruction disassembler and use it to guide the general disassembler logic. But how does this recursive algorithm generalize to other executables coming from the same compiler, from other compilers, or compiled for other architectures? Of course, there is a usual problem with recursive disassemblers. Control flow cannot be always followed. And we'll come back on this later, but that's actually only one of the problems with the previous disassembly algorithm. Because we made a series of questionable assumptions during this manual disassembly, and I'm going now to explore a few of them. So the first one, and you certainly have noticed it, was to suppose that routine call always returned to the caller. When we disassemble the call instruction, we continue analyzing the fall through, assuming the call routine will eventually return. But in reality, there are non-returning routines, and there is no need to go very far to find an example of that. In Visual Studio C runtime code, which is statically linked in our Windows executable, there are several calls to APIs terminating the execution and therefore never returning to the caller. And the compiler knows that these APIs do not return, so it can emit code padding just after the call. Like here, there is a call to exit process, and the int3 just after is not supposed to get executed, and therefore should not be disassembled as part of a routine. So from a disassembler perspective, how do we know which APIs do not return? It's in the prototype. In the full prototype, there is a specific attribute that tells us that this exit process API is not returning. And note that returning void and being non-returning are two different things. Another example of non-returning routines are infinitely looping routines. Here is an example from some GCC library code. So this routine is non-returning because it has no way to go out and come back to the caller. So let's think a bit about these non-returning routines. We need to identify them if we want the CFG to be correct. For the non-returning external APIs, like exit process, we can identify them from their names if we have the knowledge somewhere of their full prototypes with a non-returning attribute. Now, for the non-returning internal routines, for example, imagine a wrapper routine simply calling a non-returning API, we need to analyze the graph, the control flow graph. And if the graph has no way to go out, no returning blocks, then it is a non-returning routine. And this last point brings an interesting situation. We can only know an internal routine is non-returning after having analyzed it. So what if we are on a call and we do not have analyzed the target yet? Can we continue analyzing the fall-through? We could stop analyzing the caller and analyze the callee first to see if it's returning or not. But the thing is, maintaining the caller state could be tricky. There might be a possible state explosion situation with a chain of calls, possibly coming back to the caller. And more importantly, often we do not even know where the callee is. There are some non-trivial calls, and we'll come back on that later. So we have to take a decision without knowing the actual target of the call. So the way we deal with that in JEB is the following. So for the external APIs, we have a C parser to parse the compiler SDK header files, and this parser builds what we call type libraries, and these type libraries provide for each declared function its full prototype with the non-returning attribute if present. So we got type libraries for several major compilers and SDKs. For internal routines, we first try to identify simple cases at the time there is a call that gets disassembled. So for example, we have simple binary checks to see if the callee routine is a trampoline to an external API. And if it is, check if it is a non-returning API, and then if it is the case, we do not disassemble the fall-through. Otherwise, we terminate the analysis of the caller, assuming the callee returns. So exactly as we did in the simple recursive example. So then later, when we analyze the callee, if we found out that it's actually a non-returning routine, we reanalyze all the callers with this new information. And that's not always easy to do because it comes back to undoing the first analysis of a caller, and a complete routine analysis can be hard to undo properly. So the second assumption we made was to consider that routine control flow graphs are necessarily distinct. When we had no more addresses to analyze for the routine one, we consider it done, like if we were not to touch its control flow graph again. But in reality, it can be more complex. For example, there is a case of two routines sharing code. Once again, it comes from Visual Studio x86 C runtime code, so nothing particularly exotic. Notice how the routine on the left branches in the middle of the routine on the right. So why is it a problem for us? Let's say we pass the routine 1 here first. So we build its control flow graph, its basic blocks, and then we pass routine 2 and found out that there is a branch within an existing basic block. So the instructions in red are shared between the two routines. Now the question is, do we duplicate this instruction into another basic block and build a separate control flow graph for routine 2? Or do we split the existing basic block we previously built such that we share a new block between the two routines? So first, let's remember the usual definition for a basic block. It's a series of instructions executed in a row, and as such, it is a super useful abstraction for later analysis, because basic block can be processed without dealing with possible control flow changes. There are no control flow changes within a block. Of course, there is an exception to that. Exceptions, they actually break the flow within blocks, but let's focus on a standard situation. So if we were to duplicate the instruction, then we would have several possible basic blocks at the same address. And it will make the writing of later analysis harder because all these blocks will need to be analyzed at the same time when looking at one address in particular. So in other words, there wouldn't be just one control flow representation at a given address. So it's likely not a good idea to duplicate instructions if we want to keep the usefulness of the basic block abstraction. So the way we deal with that kind of situation in JEB is that during the disassembling, we build what we call skeletons, basic blocks. These are simple containers for instructions, and they can easily be modified. And we split them when needed. For example, when we found out that there is actually a branch coming directly in the middle of a block. And once the whole disassembly is finished, we build final control flow graphs from the skeletons with proper basic blocks. That means that in JEB, an address belongs to at most one basic block, and basic blocks can be shared among routines. So that's what the previous example looked like in JEB. There is a shared block between the two routines. Another assumption we made during the step-by-step disassembly was to consider that branch instructions immediately end basic blocks. And as soon as we disassembled the conditional branch, we terminated the current block. That's the usual definition of basic block, right? They terminate on branches. There is an iconic counterexample of that. If we turn to other architectures than x86, and remember that's our goal, we intend to disassemble several architectures. So this example is branch delay slots, which is a feature present on MIPS architecture, but also on several others like Spark. So there is some MIPS assembly code, and in this snippet I want to focus on these instructions here. These are conditional branches, that is, they branch or not depending on a certain condition. Now, if you have never seen MIPS code, the tricky part is the following. The fall-through instruction of these branches, here in red, are always executed when the corresponding previous conditional branches are executed. In particular, even if the condition is true and the branch is taken to go elsewhere, the fall-through instruction gets executed. So the purpose of this CPU feature is to avoid guessing which instruction is the next one when executing a conditional branch. That is to avoid having a pipeline bubble in case the guess was wrong. So on this CPU, when a conditional branch is executed, the fall-through instruction, actually any kind of branch is executed, the fall-through instruction is always executed. And in the end, that's the job of a compiler to put instructions in the delay slot. So sometimes these are just NOPs because it couldn't find anything interesting to do with the delay slot. So from a disassembler perspective, why do we care about this? Let's focus on this particular snippet here. It contains a conditional branch, BEQZ. So we have to cut a basic block somewhere to indicate that there are two possible control flows. And once again, a basic block is a series of instructions executed successively, which means the delay slot instruction belongs to the same block as the branch, as it is executed every time the branch gets executed. But if we cut just after the delay slot, we now have branch instruction in the middle of basic blocks, or at least not in the last position. And this is basically breaking one of the most common assumptions made by binary analysis tools and users when dealing with control flow graphs. Basic blocks end on branches. So at first, we might be tempted to see if we can avoid that. For example, we could say that because the CFG is just a representation of the code, maybe we can switch the order of the instructions. That is, put the delay slot before the branch in the graph, just to keep branches in last position. Of course, if we do that, we would actually break the order of expression evaluation, because the condition of a branch needs to be evaluated first. And for example, here in the graph with the instructions order reverted, the V0 register is set to the constant value 1 first with the delay slot instruction, and then the conditional branch uses the same V0 as a condition. So it's no more a conditional branch, we just broke the code logic. Another idea would be to introduce a macro instruction, something pretty common in MIPS assembly, to represent both the branch and the delay slot at the same time, such that we still have a branch in last position. Again, not really a good idea, especially because it's actually legal to have another branch coming directly on the delay slot instruction, and it's not something that we can handle easily with the macro instruction. So there are no shortcuts, as far as I know. We have to allow branch instruction in the middle of basic block, and that's what we do in JEB. And that's the job of the instructions disassemblers, to provide the number of delay slots for each branch instruction, because there could be several delay slot instructions. That's just a feature of the architecture, the depth of the pipeline. And there is an example of a MIPS snippet and its corresponding control flow graph in JEB, so you can see all the branches are not in the last position. Another assumption we made was that the instruction set remains the same for a given binary. That is, the way machine instructions are encoded and which machine instructions are available should not differ in a given executable. There is a strong counterexample from the ARM architecture. There is a snippet of assembly code for ARM processors, and here we got a routine call to this three instructions routine. So these two routines actually use different instruction sets. The left one uses the thumb instruction set, while the right one uses the ARM instruction set. So these are two different instruction sets sharing the same encoding space, which means that the same bytes will possibly be decoded into different instructions. In itself, it's not a problem, but the thing is they can be both in the same executable as in this example. So how does the CPU knows which instruction set to use? In this case, it knows he has to switch from thumb to ARM thanks to a BLX instruction with an immediate operand. BLX stands for branch and link and exchange instruction set. So for a disassembler, that means that we have to make sure the instruction disassembler can actually handle multiple instruction sets. And it also means that knowing an address is code and not data is not enough anymore. We also have to know which instruction set to use when disassembling at this particular address. And the information can come from various sources, like, for example, the way the address is called, armBLX with an immediate, the way it is referenced, elf arm symbol with least significant bit set to 1 is a firm address, the way the address is aligned, etc. So in JEB, instruction disassembler can handle different instruction sets and we switch from one to another based on information provided by the disassembler. So the general disassembler logic collects ints to switch the instruction set. Now, if we have an unknown code address, that is, we know it is code, but we don't know which instruction set to use, we order the possible instruction sets from the most likely to the least likely with a bunch of heuristics, and we try them in that order until we get something satisfying, that is, we get an actual proper routine. Now, the big assumption we made during the manual disassembly is that we supposed that the control flow can always be followed. And when we were analyzing the routine call, we stored its target for later analysis. That is, we assumed the target was necessarily known to us. Of course, this is not always the case, and that's the usual counter-argument against recursive disassembly, as I said at the beginning. And this control flow problem has been visited again and again. And so here I just want to give a glimpse of how we deal with that in JEB. And as you're going to see, it's not a one unique solution, but rather several techniques combined together. So first, to clearly illustrate the problem, let's explore a classic example where control flow is hard to compute, jump tables. So jump tables are used by compilers to implement switch statements when the case values are close to each other, so when there are no gaps between them. So for example, there is a switch statement in C with all cases between 1 and 400 defined. And if we compile this code with Visual Studio and disassemble it with the simple recursive algorithm, we end up with this graph. So obviously, we are missing a lot of code here. Actually, all the case handlers are missing. So what we have is an indirect branch on the left, and this branch is accessing an array of 4-byte addresses using the ECX register as an index. So here, the basic recursive disassembler cannot follow the indirect branch because the instruction disassembler cannot provide the targets, as it is not encoded in the instruction itself. So that means that if we want to discover the possible control flow here, we have to find the possible values for ECX at this particular instruction. And then we will get the possible next addresses to execute, but should be executed by reading the values in the table and by assuming that will not be modified in the meantime. So, and finding the possible values for ECX seems doable because there is an actual comparison on ECX just before this block, constraining the possible values for ECX. So the general question behind that example is how to find possible values for indirect operands, that is, any operand based on register or memory whose value is not encoded in the instruction. And we need those values in particular to find the possible targets of indirect branches and to improve recursive disassembly results. In other words, for a better control flow, we need a better data flow, which is a classic situation in program analysis. So as a first try, let's see if we can answer this question in a syntactic manner, that is, just by doing some pattern matching on the assembly representation. And that's what we are doing in JEB to build the control flow for the x86 Visual Studio jump table I've just shown you. So to give you an idea on how such thing can be implemented, there is an extract of the code. So the first step is to check if the given instruction is a jump with an indirect operand, following the usual pattern for a jump table with 32-bit addresses. And if it's the case, we retrieve the jump table address from this instruction. Then the next step is to look at the basic block just before the branch, check if it contains a comparison between the index register previously found and a constant. And from that comparison, we can find the number of entries in the table. That's the constant. From there, we can read the jump table from memory and find out each case handler address, each entry in the table. So note that in reality, the parsing is a bit more complex because there could be a secondary jump table with 1-byte entries when there are a few gaps between the case values. So there could be 2 jump tables to parse, actually. We also have a similar code for that. And the final step is to take the case handler addresses. We can disassemble them. We know it is code, and connect the resulting basic blocks to the indirect branch node. Also, we define the jump tables as array of addresses to prevent disassembling it. So the point I'm trying to make here with all this is that it's not particularly difficult to implement that kind of parsing. We only have to understand precisely the constructs used by the compiler. Now, at this point, you might feel a bit outraged to see a complex problem such as control flow reconstruction tackled with such basic syntactic approach. Clearly, it's not elegant, and it is very specific to the compiler and the architecture. Nevertheless, I would argue that sometimes such approach might be acceptable when the target code is very common, like the Visual Studio x86 jump table implementation. It's in a lot of binaries out there. So dealing with it in a syntactic manner has some advantages. The development effort is limited, and more importantly, it provides excellent parsing performance in comparison to the more heavy approaches I will describe later. Here we are just doing some pattern matching. Obviously, syntactic solution cannot scale, especially in the context of a multi-architecture disassembler, where we have to deal with a large number of situations where the control flow is hard to compute, depending on the architecture, the compiler optimization level. And it's not only a diversity problem. There are cases where pattern matching is clearly inappropriate. To illustrate that, let's look at another example. If you disassemble a ELF MIPS executable, you will likely see something similar to this at the entry point of a program. At the end here, we have an indirect branch, jump and link on the register using the T9 register as a target. So where does this branch go? To answer that, we need to find the possible values for the T9 register at this particular instruction. So let's go backward. T9 is loaded with a value depending on GP register, the global pointer, which itself was set here at the top after some computation using the RA register, the return address. And the RA register has been set here by the branch and link instruction at the entry point. So in order to find the possible targets at the indirect branch at the bottom, we need to be able to follow all these instructions from the entry point and to analyze them to compute the correct values. So that includes dealing with arithmetic operation and branch logic. So clearly, pattern matching seems not suitable here. And this thing is not an exotic case. It's really the jump and link on register T9 is the classic way to implement routine calls in MIPS. It's defined in the System 5 ABI for position-independent code, which is used in most Linux MIPS executable out there. So back to the original question, how to find possible values for indirect operands, and especially when syntactic solutions are not suitable, like in the MIPS case. So one way to tackle this in a non-syntactic way is to simulate the routine execution, such that we build the machine state, that is possible values for registers and memory between each instruction. And if we can do that, then we can actually directly solve the indirect operands. But for this to be possible, we need to have the actual semantic of machine instructions. That is, we need to know what each instruction is doing, such that we can update the machine state. And of course, this kind of simulation is not always possible, due in particular to unknown inputs, but it might help solving some cases in a generic way. So the very hard part here is to get the semantics of machine instruction, which is yet another classic problem for reverse engineering tools. Luckily enough, we already have it in JEB because we need the semantics of machine instruction for decompilation. So it's time to introduce the JEB intermediate language. That's the intermediate representation used by the decompiler, by the native decompiler. And even if it's talking not about the decompiler, I will briefly describe it in order to understand the next steps. So the JEB intermediate language can be seen as a low-level imperative language made of expressions, and there are 16 different expressions. So you can see here the corresponding Java interface. Each expression can contain sub-expressions stored in a tree-like structure, and the statements are the highest level expressions. So when you convert a routine, what you get is a CFG of IL statements. Now, the main purpose of this intermediate language is to allow us to express the semantics of native instruction. So for example, there is an x86 instruction, a XOR between EAX and memory slot, and its corresponding semantic representation in JBIL. So all the side effects of the native instruction are made explicit in the semantic representation. In particular, there are the flags updates. Of course, many of these side effects are often useless in the sense that they do not impact the runtime behavior, so they will be removed during the decompilation by the optimizations. So the heavy lifting is done by the converters, whose job is to make explicit the semantics of the native instruction into the JBIL. So you can see here the converters we currently have implemented. Now, back to the idea of simulating native routines to improve the disassembly. As we have access to these native to IL semantic converters, we can implement the simulation on the intermediate language. And it has at least two strong advantages. Implementing the simulator is going to be pretty easy because we only have to handle the 16 IL expression, especially in comparison to simulating all native instructions. And all architectures for which we have a native to IL converter will benefit from this simulator. On the other hand, it will have some performance cost because the IL translation needs to be run before the simulation. So that's what we do. First, each routine is converted into its semantic representation in IL, and we obtain a CFG of IL statements. So we do not run the decompiler optimization at this point because it would be too costly for performance. The disassembly as fast as possible. So for example, here is the first basic block of the IL CFG from the main of our Windows executable. So you can see here all the side effects of the instructions without any optimization. So the second step is to do the actual simulation. So we start from a clean state with pseudo-realistic values in registers, and we allocate memory for the stack in particular. Then there is the actual simulation of each IL expression. So each expression implement a special method, which is the evaluate method you see here. And this method takes in input the current state of the machine, and the state will be updated during the evaluation. And it returns an immediate, a constant. So what we are doing here is really a concrete evaluation of the expression. To give you an idea, there is an extract of the code to evaluate an operation in JBIL. So first, you can see the first two lines. These are the operands that are recursively evaluated to get their concrete values. So these operands can be pretty complex expressions themselves. And then we do the actual computation depending on the operator. So overall, the simulation logic is to start from the routine entry point and follow the control flow by evaluating each statement. And this simulation is intended to be safe, in particular when we cannot evaluate an expression because something is missing. For example, it uses an uninitialized memory slot. We abort the simulation. We do not try to continue or anything. We want it to be really safe. Also, we do not do recursive simulation. We only simulate one routine. So when there is a call to a subroutine, we consider that all registers are spoiled. So that is, they are now unknown. And the final step is to use the values computed by the simulation to enrich the disassembly, in particular by solving the indirect operands. So let's come back to the MIPS example. Here is the code before the IL simulation. And after the IL simulation, we report the concrete values we found during the simulation to the disassembler, and we also print them as comments in the UI for the user. So the comments starting with pre contain register values found by the simulation before the corresponding instruction is executed, while post comments contain register value after the instruction. So for example, here is the value of T0 before this instruction, and here is the value of T9 after this instruction according to the simulation. And this value is the target of our indirect branch at the bottom. So now this next routine will be disassembled by a recursive disassembler. So we explained that the IL simulation is not a silver bullet. It remains a concrete emulation that works only when all inputs are known. So what if we cannot follow the control flow from the main routine in our toy example? Do we have another way to find the secret algo routine, which is somewhere in memory, without any reference on it? And that brings us to another old program analysis question. Is there a way to distinguish code from data just by looking at it? In theory, that's a well-known intractable problem, like anything interesting in program analysis, so it's not really helping. In practice, it is indeed a hard problem for most architectures, because code and data share the same memory space, and because almost any values can correspond to a machine instruction, due to the fact that most instruction sets encoding are very dense, that they tend to use all possible values. So there is no clear way to know if a series of bytes is code or data at first. But the context can help. And to illustrate that, here is a raw dump of an x86 executable compiled by Visual Studio. Now, if we ask, is it code or data? If you are used to reverse on Windows, you certainly notice some patterns here. These 3 bytes correspond to push EBP, move EBP, ESP, the classic Visual Studio routine prologue. Then we got these 2 bytes corresponding to pop EBP ret, the classic Visual Studio routine epilogue. And we also got a sled of CC bytes, that's the classic Visual Studio code padding. So knowing the compiler, this really looks like code because it follows the patterns and structure of Visual Studio code. There is another example from a different perspective. That's the memory view of a x86 executable compiled with GCC. We already identified some code areas and some data areas. So now we wonder if these gray areas are code or data, and we don't have any reference on it. Once again, knowing the compiler can help answer these questions because GCC for x86 usually does not mix code and data. So therefore, the top area is likely code, while the bottom area is likely data. So you got the idea. What we do in JEB is that during the analysis, we try to identify the compiler that serves to create the executable. And then we apply some compiler-specific heuristics, and to solve in particular the code versus data question. There is an example of an heuristic. An unreferenced address A is considered to be likely code. If all this is true, the compiler identified is GCC or cloud, the architecture is x86, there are no obfuscation or malformation in the file. So once again, we got a bunch of heuristics to check for that. And the address lies in the code area, defined from the file sections. And the bytes at A do not look like code padding. Once again, a compiler-specific heuristic. Now, an interesting design question is how do we integrate such compiler-specific logic in a so-called generic disassembler? So what we do in Jeb is that we load different extensions depending on the identified compiler, the file format, the architecture. So you can see some of the extensions we have here. And so the disassembler engine does not know which extensions were loaded. It just queries them for some heuristics. And there are a few of the heuristics. Check if one area looks like code padding or like a routing prologue, or if a specific instruction looks like a switch dispatcher. So that's where the Visual Studio x86 specific logic I shown before is implemented. So we got around 20 methods like this, and internally the extensions are ordered by priority, and the disassembler talks to a manager, an extension manager. So each extension can decide to provide a result for an heuristics or to let the following instructions try their own heuristics. And with this extension system, we can also quickly tweak the behavior of the disassembler, for example, by loading a custom extension with a special priority. So of course, these compiler-specific heuristics will be wrong at some point. It can happen because we misidentified the compiler, because there's a new or old compiler version for which our heuristics do not apply anymore, or because there are some obfuscation that we missed. So what we have is a feedback loop in the disassembler. First, we log the errors during the disassembly. So for example, an error would be trying to disassemble a series of bytes that does not correspond to an instruction, or for example, failing to build a routine because the control flow graph is incorrect, there is a branch in the middle of an instruction, something like this. And then, if too many errors were made, we switch back to a safe mode where only very conservative heuristics are applied. Finally, as a last resort, it is an interactive tool, so the user can tweak the disassembler decisions. And the final assumption we made during the step-by-step disassembly that I want to review is that we supposed that all code matters. And so actually, this assumption is a bit different from the others. It's not really that we wrongly assume something, but more than something important is missing in the basic disassembler. To illustrate that, let's come back to the toy example. As you might remember, secret algo routine converts its string argument into an integer using the A2I library routine. In the output of a disassembler, there is a corresponding call to an internal routine because A2I was statically linked in our executable. And A2I is actually a pretty complex routine, separated in several subroutines, but it's just the standard library routine A2I. So that brings us to one of the oldest reverse engineering problems, identifying library routines. And obviously, such identification is super useful for users as it allows reading the documentation rather than analyzing the code. And it is also useful for automatic analysis as it provides useful information like the prototype of the identified routine. Otherwise, the decompiler, for example, has to guess the prototype, which can be non-trivial, to say the least. So the way we handle that in Jeb is pretty standard. We generate signatures to identify library routines. So we process in input files containing named routines, for example, object files provided with static libraries, but also executables with symbols, or even Jeb projects, but it's file already analyzed in Jeb. From that input, we generate signatures that will be used at runtime by the disassembler to identify routines. So let's dig a bit into the signatures. They were designed in a generic way, and they can be seen simply as containers to identify what we call an item, which is anything possibly defined in the Jade native model. So routines, basic block, data blob, anything. The signatures contain two things, a set of features, which are the characteristics of the item serving to identify it, and each feature can be compared against another. And then a set of attributes, which represent the knowledge we have on the item, like its name, its origin. To give you an example, here is what we have in the signature for the memcopy routine from Visual Studio 2008 static standard libraries. So two features are used, the size of a routine and a custom hash I will describe later. And then there are the attributes representing what is known about this routine. So now the interesting question is, how do we select the features? Here, we want to identify compiler static libraries routines. So we would like to have no false positives, because the Jeb decompilation pipeline first, that is the steps after the disassembly, are going to rely on the signatures, for example, by using the prototype of a routine. And users are going to rely blindly on the signatures as well. They will trust that the routines identified and renamed as library routines in the UI are indeed the library routine. They will not double check. And note that in this context, a false positive happens when a match signature does not convey the original routine behavior. So for example, if we have two routines with different names but the same code in a library, like memmove and memcopy in Visual Studio 2013, identifying one as the other is not a false positive in this context. It's not a matter of giving the original name used by the developer. It's a matter of giving a correct name, one that describes the routine behavior and a correct prototype. And so this compiler library identification problem is one of the flavor of a more general problem of code similarity. In a different context, patch diffing, malware diffing, we would set different objectives for the signatures and maybe accept false positives to have more true positives, and also accept partial matches. So the first obvious feature to avoid false positives is the routine code. So we have a feature called routine code hash. It's a custom hash computed from the routine assembly code. And so using assembly rather than the binary code allows us to avoid generating different signatures for the same code in different endianness. That's useful for architectures with possibly different endianness like MIPS. And the current hashing algorithm is pretty simple and produces a 64-byte hash. And note that the algorithm is almost the same on all architectures because it processes the past assembly instructions under the generic I instruction interface. So one tricky part of the hash computation is that we have to abstract away the parts of the instructions that rely on their actual location in memory, such that the same routine mapped at a different location will yield the same hash. So here is an example from an x86 object file. The values in red here are absolute memory addresses pointing to external symbols. And in an executable, the same code will have different addresses here. So we have a normalization step where we abstract away the absolute addresses, and then we compute the hash. So actually, we abstract away all the constants to be safe. And note that sometimes the normalization can be more complex. For example, there is an ARM relocation that can change the actual mnemonic between object files and executables, so we have to normalize them as well. That being said, routine code hash might not be enough to distinguish different routines and avoid false positives. There is an example of two Visual Studio library routines. Their code is the same, so their hash will be the same, except that they call a different subroutine, which implement a different logic. So the actual behaviors of these two routines differ. So we need to distinguish them. And so we introduce another feature in our signatures, the names of the called routines. Once again, the previous features might not be enough to distinguish different routines. For example, here are two routines with the same hash and the same call routine. The only difference is a 4-byte constant. And by default, this constant will not be considered during the hash computation. We remove all constants. So to distinguish these two routines, and they are really implementing a different behavior based on the constant, we have to reintroduce this constant as a feature. So we have all these possible features, and I've shown the main one, but there are more. So how do we select the ones to put in each signature? What we do is we start with a minimal set of features for each sign routine. So that's the routine code hash and the call routine names for small routines, as the hash is likely not enough to distinguish small wrappers. So this is the starting set of features. And then we compare with the routines of the same library. So if no other routines in the library has the same features, we consider that the current features are good enough and we keep the signature as is. But if there is a routine with a different name and the same features, we consider it to be a collision, and we try to solve it by inserting iteratively new features, like the call routine names, the constant values, until the collision is resolved. That is, the two signatures have different features. And note that if we cannot resolve the collision, but we still generate an unknown signature. That is a signature that says it's likely a library routine, but we don't have any specific information on this routine. And also the users can actually solve the conflict manually by setting the best signature. And so there are two strong approximations behind this approach. First, the set of routines from the same library is considered enough to see if a signature uniquely identifies a routine. And then we consider the routine name to represent the behavior. That is, different names indicate possibly different behaviors, which is something that is not always true. As a final note, let's mention that there are some routines that do not have particular features to distinguish them. That is, for example, very small routines like this one. So for them, we have another hint we can use, their location. So what we do is that we sign these routines with basic features, but we do not use these signatures by default during matching. Now, if we happen during the disassembly to have a particular memory area with a large number of identified routines from the same library. Then we apply these untrusted signatures for this library in this particular memory area. So what we are using here is the fact that the linker will usually put the object file from the same library in an adjacent memory range. So in this range, we can be more flexible. So to conclude on signatures, at this point, we have more than 200 signature packages for different compilers, versions, architectures. So you can see a few of them here. And Visual Studio was really the primary target. So that certainly explains some biases we have regarding the signature generation problem. Regarding the matching logic, so during the disassembly, we load in memory signature packages based on the identified compiler, and then each routine is tentatively matched. Also, user can generate their own packages, either from the UI or in batch mode. So enough with all these broken assumptions. What is the point I'm trying to make? So if we sum up what we did, originally we successfully disassembled our Windows executable, secret.exe, with a simple recursive algorithm. But we made a lot of assumptions on the way. And then we showed that many of these assumptions can be broken just by looking at standard compiler code. I've not shown examples from obfuscated code, packers, protectors. All examples I've shown come from classic modern compilers. And you probably have in mind a tons of overbroken assumptions we made. Instructions do not overlap, code is not self-modifying. So it's actually the way many obfuscation techniques work, by breaking the assumptions made by analysis tools. So a first conclusion will be that there is no such thing as a disassembler able to correctly disassemble all programs for all architectures and compilers, which shouldn't come as a surprise to you, I guess. So the intuition behind that is that there are no interesting assumptions that are true on so many diverse programs. And if you are an academic, there is certainly a link to make with the halting problem and its generalization, the Rice theorem, which basically says that there are no interesting properties on a program's behavior that can be decided. Okay, we cannot disassemble correctly all programs, but we might still be able to do okay on a subset of them. And what we can do is to divide the universe of programs into groups. And for each group, we should have a reliable way to check if a program belongs to it or not. And then a set of interesting assumptions that we know are true for this whole group. That's exactly the idea of compiler-specific heuristics I described before, but it can be more precise than that. You can have a group that is a specific compiler version with a specific static library from a specific high-level language. And then when a program does not belong to a known group, we apply only very conservative assumptions. That's one of the ideas behind the JEB disassembler design, and there is a very simplified view of its workflow. So at first, there is an initialization step during which the executable, the file format is parsed, and then the compiler is tentatively identified. And from there, we instantiate what we call the strategy and the disassembler engine. So the strategy contains the extensions I previously described and the gap processors. So the gap processors are in charge of disassembling the unanalyzed memory areas. And there is, in the middle, an error manager which can tweak the loaded extensions and the gap processors if too many errors were made. In the disassembler engine, the first step is a very classic recursive disassembling. And then we attempt to process the remaining gaps, the unanalyzed memory areas. And finally, the CFGs are built. Then we run the IL simulation on these routines, which can find more routines, so we can re-enter the disassembler engine. And the final step is the signatures matching, which can also re-enter the disassembler engine. So for example, when a signature tells us that a given routine is actually non-returning, we reanalyze its colors. So to come back to the initial classification of disassembler, at its core, the JET disassembler remains a recursive disassembler. But under certain conditions, it will behave almost like a linear disassembler, because all gaps will be considered code, for example, depending on the strategy, that is, depending on the identified compiler, the architectures, etc. So just a few final words on how to make the process of dividing the programs into groups easier for developers. It helps a lot if the disassembler is coded in an informative way, that is, it explicitly reports when an assumption is broken, because then the disassembler helps mapping the program universe by identifying corner cases as soon as we open a binary. Of course, there is a need to proactively and thoroughly test the disassembler to refine the group definitions on diverse sample sets. So there are a lot of different features that can be tested with a disassembler: the routine entry points, the CFGs, the basic blocks, the instructions. And building a diverse sample set that is with many compilers, optimization levels, source language is a non-trivial thing, and especially because most of the available samples out there are just not classified. We do not know the compiler optimization, etc. So we have to compile a lot of samples on our side. Also, it really helps when user report sample. Often the fix is just to tweak the groups, the group definition. And on the other hand, the disassembler should provide the user the ability to fix the broken assumption from the UI. So hopefully this presentation convinces you that disassembly remains a complicated problem. So we might think that the situation for disassembler will become worse and worse as new compiler versions are released, but there is an interesting trend right now where many anti-exploitation techniques tend to make the disassembly problem easier because they provide reliable hints to solve, in particular, the code versus data question. So for example, the ELF executable segments, which strictly separate code from data, Microsoft Control Flow Guard, which provides routine entry points in the key metadata, the Intel Control Flow enforcement technology, which emits special instruction at routine entry point, making the routine detection problem easier. So there should be hope. Thank you very much. If we have time for questions, yeah, sure. Okay. There is one in the back.
Hi, thanks for your presentation. One question for you. Why do you identify library functions based on their disassembly signatures as opposed to using their IR signatures?
So the thing is, so it's a good question. So as we have a full decompilation pipeline, there is a question that comes again and again. Should we use the decompiler, the next steps of the decompilation pipeline to solve problems at the native level? The thing is, at this time, it's costly in terms of performance. So the conversion step has some cost. And so really, the question was, for us, the question is it worth it? Should the user wait a bit and provide better result? So we might use some days things like that. We were really all doing, actually, we might use that, but this system was intended to be really fast. And actually, we are doing that. For example, we are doing a switch. So I showed syntactic detection for switch. There is a cool thing with when you have an optimized intermediate representation, several native implementation becomes merged into one similar pattern in the IR because we canonize the order of the IR expression and stuff like that. So we have also static signature on IR code at this point just after the optimization for the classic switch pattern. So if there is a comparison and then an indirect branch, and for example, we can detect the ARM implementation and the x86 implementation with the same IR pattern. So we do that also, but it's really if you decompile the routine. And in JEB, we still have this separation between disassembly and decompilation. You still have to go on the routine, press tab to decompile the routine. So the IDA style X-rays separation. Someday it will probably change, maybe like Ghidra, but at this point you still have this separation. So we still need a strong disassembly to be helpful for user.
Hi. Yeah. Thanks for the presentation again. I had a question. Why did you guys decide to create a new intermediate representation instead of using LLVM, IR, or something like that, where you have tooling already?
Yeah. So I'm not the one who took this decision, but so Nicola is the architect behind JEB. But as far as I know, so it was 4 or 5 years ago, so pretty long time ago. At this time, it tested the LLVM intermediate representation. It was not like satisfied. As far as I remember. So we really designed the IR like from the particular problems we had. And in the end, right now, it's pretty simple, as you saw. So it's kind of pretty readable. It's kind of pretty easy to manipulate. So I think it was worth it to do our own stuff. I completely understand people who say, okay, there are too many IRs. But at the same time, it's a very simple language, like an assembly-like language with pretty clear syntax. And we could translate this IR to something else also. So we still have our converter using our own IL and then convert at another conversion step to be compatible with tools using LLVM IR. I'm pretty sure that would be doable, and that probably a much more simpler problem than building the converter, the actual native to IL, which is very hard part if you do it manually like we did. So.
Hi. I wonder what the size of the output IR file is compared to the assembly Is it the same order of magnitude or is it way bigger?
So you mean the number of instructions?
Yeah.
It's obviously it's much more larger, but you don't see. I mean, the first IR, the raw IR, is really large because there are all the side effects that are here explicitly as assignments. So obviously, this one is not really readable and not really helpful. But then there are optimizations. So we got a series of optimizations. So each optimization is doing something simple, and that's more the combination of optimization that in the end reduce the number of statements. So we have dead code remover, variable propagation, and stuff like that, all executing, refining the IL, and the NIL is pretty small. And then there are things like type resolution and stuff like that that enrich the IL. So I don't have numbers to the comparison, but as far as I remember, the readability of actually you can see it in JEB. You can see the final error before the decompilation. It's pretty readable, I would say, and not too large. But still, it's assignments to variables and stuff like that.
And I wonder also, since you're doing manual flag maintenance, I guess you'd have a large chunks of code basically taking care of flags every time you enter functions, get out of functions, and stuff like that. So, do you have any optimization for that?
For what? The flag update?
The flag save and restore every time an instruction can possibly change the value of the flag. Does that mean you have to test that every instruction or every function?
I'm not sure I get your point.
I'll talk
Okay,
later.
okay, sure. Okay.
Yeah, I was wondering, when you're doing the basic block building with ARM instructions, do you accurately take account of all the conditional kind of bits on the end of ARM instructions to split them apart into different blocks?
I'm sorry, I hear you very badly. So yes, the basic blocks.
Yes, so when you're building the basic blocks with ARM instructions, obviously each instruction can be conditional. So do you split your blocks apart based on conditional instructions or just on jumps?
So meanwhile the blocks are shared? Sorry, I don't get. You mean sharing the blocks between the routines?
No, just so in the same routine, so ARM instructions can be like completely conditional.
Yeah, sure, okay.
Do you split your blocks for a subroutine based on those conditions or just on the jump blocks?
Okay, so in ARM, most instructions can be conditionals. So we do not know. We present them as if they were going to be executed at the native level. There are a few tricks with that. Actually, the instruction disassembler, so they provide the flag saying, okay, this instruction is conditional or not. So we have implemented this for the ARM instruction, so we can say stuff like that. The only thing we do currently with that is that, for example, if there is a call to a terminating API, but actually the instruction is an ARM conditional instruction, we cannot assume that it will never return because we don't know if the condition is true or not at this point, just at the native level. We don't do anything specific. And then at the higher level, there are some checks on the flags status with the optimizations, like does it make sense to have the instructions, or is it really the condition is always false, for example, something like that. So we have checks for that in the higher. At the native level, it's very basic. We just consider that it will be executed, nothing special. Thanks. So thank you very much, guys.